Okay, so for this week, we're going to be looking at analyzing the convergence of the methods that we've covered so far. And in doing that, we're actually going to set the table for stuff that we're going to be doing for the rest of the semester as well, and putting things in a different kind of framework than what we've seen before. So the methods that we've looked at are the Jacobi method, the Gauss-Seidel method, and the SOR method. Now, what we're first going to do is put these in the context of a more general framework, look at how we can analyze convergence properties of those iterative schemes, apply each one of those analyses in more detail to each one of the schemes that we've looked at, and then in addition to that, see how we can further apply the analysis to the particular matrices that we've spent a lot of time looking at, mostly the ones related to the Poisson matrix, and then get an idea for like how many iterations it's going to take for this method to converge. Okay, so far we've been looking at solving systems of the form AX is equal to B, where B is the unknown. And what we're going to look at, what we're going to be able to see, is that we can actually sort of transform this system into the form LX is equal to Y, and look at a general method to solve systems like this, where this matrix L is going to be related to the matrix A. Okay, and it'll make more sense. Once I get into it, it'll make more sense on exactly what's going on. Okay, so one of the most fundamental ways that we can do an iterative method, if we have any system of equations like this, Lx equals y, one method that we can do to have an iterative scheme is called Richardson iteration, and it says the following. It says that the k plus 1th iterate is equal to the old iterate, xk, plus an updated value. In this case, it's going to be y minus L times the previous iterate. This is called Richardson iteration, and anytime you have a system like this method right here can be used to try to find a solution. Now, when I say anything, I don't just mean matrix vector solutions. So, for example, if you've seen one of the standard proofs for the existence of solutions to first order differential equations, one of those methods is called Picard iteration, and this is basically exactly this right here. Okay, so my claim is that every method we've looked at so far, we can take this system, modify it to get some other system, and write the iteration in this fashion right here. Okay, so let me just do this example for the Jacobi iteration, and I think it'll make sense on exactly what I mean by this. Okay, so recall that the Jacobi iteration is expressed in two ways. We can have dxk plus 1 is equal to b minus r xk, or if we take the inverse on both sides, we're going to get x k plus 1 is equal to d inverse b minus d inverse r x k, like this. Okay? Now, practically speaking, we never take the inverse of a matrix when we apply this algorithm, and we don't even have to think about this as being matrix vector multiplication in the first place. But as I've mentioned in the labs and things like that, the implementation of the matrix vector multiplication, or the implementation of the solution of this, is independent of the convergence properties. And what we care about in this week, and more generally in this class, is how many iterations it takes for these methods to converge. And then in another class, we can sort of figure out the best way to implement these things. That's like a whole different topic to itself. But in the analysis of these methods, we're typically going to want to just think about inverse matrices because, again, the implementation is independent of the number of iterations it takes to converge, and implementing the solution of this system with inverse matrices is easier when we're doing it theoretically than it is when we're doing things practically. Okay. So I want to make this iteration look like this. Okay, so we're going to look at, let me just write it over here. xk plus 1 is equal to d inverse b minus d inverse r xk. And again, I want to try to make this look like this iteration. Well, I see a couple of things going on. This d inverse b, this is kind of like the right-hand side of the equation. It's a modified version of the right-hand side of the equation. So my prediction is that probably this is going to play the role of y. when I compare it to this iteration here. And the other thing I noticed is that this has an xk here, and this doesn't have an xk. So essentially, I need to somehow add and subtract an xk. Not essentially do that. That's exactly what I'm going to do. So I'm going to subtract an xk and then add an xk. Okay, and if I come down here and rearrange things, I've got my xk like this, so that matches up with that. I have my plus d inverse b. This looks like it's going to match up with the y. And then what I have left is just this part right here. I've got d inverse r xk plus xk. Okay, but remember what r is. R is just the non-diagonal part of the matrix. So if if D is the diagonal of the matrix, then let me just say it over here. A is equal to D plus R. D is the diagonal part of A. R is the everything else. Okay, so what I can do over here is xk. I can write this as D inverse times D times xk. So I can write this. There was just an xk there. I can write it as D inverse times D xk. Okay, now using distributive laws on the next line, I'm going to factor the D inverse out over here, and I'm going to factor the xk out on the right-hand side. And when I do that, I'm going to get the following. I'm going to get xk plus D inverse b, and then minus D inverse. And now what's going to happen here on the inside, I'm going to have R plus D like this, and then xk over here. Okay. And now, what is R plus D? That's just A. So I have this matrix here. This is just A. And let me scoot this xk closer. Like this. Okay. So now we can match things up exactly to what we have over here. Xk plus 1 is equal to xk plus D inverse b minus this matrix times AX. Okay, so to go from the Jacobi iteration to this framework here, what we do is we take our system, AX is equal to B, and we multiply it both sides by D inverse. So for Jacobi, we go D inverse AX is equal to D inverse B. Okay, so this is what we care about. We're going to modify it, multiply both sides of this equation by D inverse to get this system right here, and then apply this iterative scheme, where now L, this is equal to my L, and that's equal to Y. Okay, so we have this general iterative scheme here to go from the system Lx equals Y. This is the iterative scheme called Richardson iteration, and one way that we can view the Jacobian iteration is to start with the system that we care about, multiply both sides by D inverse, and apply Richardson iteration to this. Okay, now for those of you who there's several of you who know about methods like this, I will give a definition here at the end of this video, but what we're doing is this is called preconditioning this system. We are preconditioning this system with the matrix D. That means we multiply both sides of the system, or both sides of the equation by the inverse of the matrix D, which is exactly what we're doing here, and then applying some iterative scheme to it. In this case, the Richardson scheme. Okay, and this is going to be the reason that we do this. Again, I will motivate why we're doing this at the end of the video when we look at convergence properties. But the basic idea is that D inverse A is going to have a better convergence property than just A. But we'll have to wait until the end of the video to see exactly what that means. Okay. So the next one that we looked at was Gauss-Seidel. And the Gauss-Seidel method, again, similar to the Jacobi method, we can write it sort of in this implicit form. dxk plus 1 is equal to b minus u xk. And here, let me just remind you, let me just remind you that A, for the Gauss-Seidel, A is equal to D plus U plus L. So D is the diagonal part, U is a strictly upper triangular part, L is a strictly lower triangular part. Okay, this is one way to write the Gauss-Seidel system. Since I don't have enough room to write everything over here, I'm just going to rewrite it by multiplying both sides by the inverse of D plus L. Okay, and so when we do that, we get that x k plus 1 is going to be equal to D plus L inverse B minus D plus L inverse U xk, like this. Okay, and now if we try to match this up with what we have over here and kind of think about how we did things before, what we see here is that D plus L inverse B is going to be playing our role of y, which means what we're going to be doing is preconditioning this system with the matrix D plus L. That might help us guide how we're going to make some of these algebraic manipulations to get it into this form right here, or to recognize it as being in this form right here. Okay, well, similar to what we did before, we're going to begin by adding and subtracting xk to this. So plus xk minus xk, and then if we continue down, I'm going to move my equal sign all the way over here to make sure I have enough room. I'm going to have the kth iteration plus D plus L inverse B. Okay, so xk matches with that, xk there, and then D plus L inverse B matches with the y. Now you just need to somehow make everything over here match up properly. Okay, so we're going to have minus, okay, so inside the brackets here, what's going to happen? Well, I'm going to have a D plus L inverse U. Then I'm also going to have this plus xk. So I'm going to have an xk here, but I can write it like this. Okay, so I have D plus L inverse times U times xk, and then the identity matrix times xk. So that's what we have going on here. Okay, just using the distributive law. If you distribute this on the inside, that xk is going to be with the u, so you're going to get that term, and then the identity times xk is just xk. Okay, but now we can do something very similar to what we did before. The identity matrix we can write as D plus L inverse times D plus L. And so actually we can write this as like this. Okay, great. So now I've got a D plus L inverse I can factor out. So I'm going to go down to a new line now. xk plus D plus L inverse B. And then we're going to have minus D plus L inverse. And then what's going to happen on the inside here? Well, when I factor out a D plus L inverse from this term, I'm going to be left with the U. And over here, when I factor out a D plus L inverse, I'm going to be left with D plus L. So I get U plus D plus L times xk. Okay, well, U plus D plus L, that's just equal to A. And so now what we have is xk plus D plus L inverse B minus D plus L inverse AXK. Like this. Okay. And so now we can make this match up with the Richardson iteration scheme here, where the xk corresponds to xk, the y corresponds to D plus L inverse B, and the L corresponds to D plus L inverse A. Okay, so for Gauss-Seidel, what we do is we take the system that we care about, which is AX is equal to B, and we multiply both sides of it by D plus L inverse. Like this. And now we apply the Richardson iteration scheme to this updated system. Or again, we call this a preconditioned system. We take the system that we care about, multiply it by the inverse of a matrix, and that's what we call a preconditioned system. Okay, so one idea to keep in mind here is that we have this iterative scheme that applies to this, and we don't apply this iterative scheme directly to this system. We take this system that we care about, precondition it, and then apply an iterative scheme. So there's always going to be sort of two things that happen with the iterative methods. We have the iterative method, which is this, and then we have the system that we apply it to. That is, how are we going to precondition the system that we care about? Okay, and the way that we precondition the system is going to depend on the exact iterative method that we're using. Okay, but for us, for right now, we're just looking at these Richardson iteration with these three examples that we've seen. Okay. So finally, the next one we're going to look at is going to be the SOR method. Okay. So again, the way that we write the SOR method, well, there's several ways that we can write it. Sorry, I just realized I have a weird error here in my notes. But anyways, we're going to have xk plus 1 is equal to omega times d plus omega L inverse B, and then minus d plus omega L inverse times omega U plus omega minus 1 d, and then xk here. So let me just read out what this is. This is xk plus 1 is equal to omega. This is d plus omega L inverse times b, and then minus d plus omega L times, inverse times omega U plus omega minus 1 d, and then this whole thing right here times xk, the value of the old iterate that we are updating. Okay. And again, what I'm saying is we can put it in this format here. So again, matching things up like we've done before, it seems that this is probably going to be our y, and we're going to have to add and subtract xk, and so on and so forth, and that's exactly what we're going to do. Now, we're going to write this as xk. So I'm adding an xk over here, and I'm going to subtract it out over there. So plus omega d plus omega L inverse b, like this. And then what I need to do is I need to subtract an xk from over there. So I've added an xk, so I need to subtract off an xk. So we're going to have minus d plus omega L inverse, and then inside the parentheses here, omega U plus omega minus 1 d. But now if I'm subtracting off an xk, notice what I need to do here is plus d plus omega L. And then all of this is going to be multiplied by xk. Okay, so why does this work? Well, if you take this d plus omega L inverse and distribute to here, you're going to get the identity matrix, and then plus xk is just going to be xk. And we don't have that term up there, and there's a minus sign. So in other words, xk minus this times that gives me 0. Okay, but now notice what I can do in the parentheses over there. Okay, so some things are going to clear up over here in the parentheses for me. We just have to make sure I get everything here correctly. Okay. so there's going to be some terms that cancel. So notice we have an omega d, but we also have a minus d and a plus d. So those are going to cancel. And then so what we're going to have is an omega u plus omega d plus omega L times x to the k. Okay, well this is really good because u plus d plus L, that's just equal to a. And so now this is going to be omega a. And so now we can write this as x to the power of k plus omega d plus omega L inverse times b, and then minus, notice what's going to happen. There's an omega here. I can factor that out. And we're going to get omega times d plus omega L inverse, and then we're just left with u plus d plus L, which is a, and then we can multiply this by x to the power of k. Okay, so again, we now see that we have put it in that framework over there, where this is our L matrix, and this is our y vector. Okay, so now what this tells us is that for SOR, one way, not the only way, but one way we can conceptualize what's happening with SOR is that we take AX, we precondition it to get omega times d plus omega L inverse AX is equal to omega times d plus omega L inverse B. Okay, so we take the system that we really care about, AX equals B. We precondition it, meaning we multiply both sides by something, by the same thing. We precondition it to get to this system, and then apply this Richardson iteration. Okay, so this shows that every method that we've looked at can be brought into this framework here. And so now we're going to analyze convergence of this iterative scheme. And now we're going to get to use some of the stuff that we learned from our first chapter. Or what was it? The chapter on linear algebra. I'm pretty sure that was the first chapter. Okay. Also, I'm going to use a different marker because this one seems to be not working so well anymore. Okay. So we're going to begin. We're going to let E k plus 1. This is going to be defined as the error. Let me make sure I get the sign here correct. Okay. This is going to be the error between the approximate xk plus 1, that is the approximation to the solution, and I'm just going to say x is the actual solution. This is the actual solution. So ek plus 1 is just the error. It's the error between the current solution, or the current approximation, and the actual solution. And what we want to do is we want to show that this error is going to go to 0 no matter what initial vector we start with. So we want to show that this error goes to 0 no matter the initial vector that we begin with. Okay, so here's what's going to happen. Xk plus 1. Well, we know what xk plus 1 is. We have a formula here for xk plus 1. So we're just going to plug that in. So xk plus 1 is equal to xk plus y minus L times xk, and then minus x. Just minusing x there. Okay, but what do we know what y is? Y is a solution to Lx is equal to y. So then y is equal to L times x. So I can write this as xk plus Lx minus Lxk, and then minus x. And now what I'm going to do is I notice that I have an xk and a minus x, and an Lx and a minus Lxk. So I'm going to collect the terms in the following way. I'm going to have xk minus x. So my goal here is I want to get some EKs on the right-hand side. What I want to do is I want to give a formula for ek plus 1 in terms of ek. So ek minus x, well, that's just, xk minus x, that's just ek. And then over here, I'm going to have minus lxk minus lx. Okay, so lx minus minus, I get lx, then minus lxk. Okay, well, what is this? This is just ek. And then minus, well, L is a linear operator. So I can factor out the L, and I have L applied to ek. So minus L ek. Or I can write this as I minus L ek. Let me try to be consistent with my vector arrows there. Okay, so in general, notice I can now apply this same argument to ek. So in general, what this tells us is that ek plus 1 is equal to I minus L to the power of k plus 1 times the first error, E0. Okay, now again, we want this to converge to 0 no matter what this initial error is. The initial error is just going to be, we pick our initial iterate, x0. E0 is just going to be x0 minus the actual solution. Okay, so we don't know what that's going to be. Obviously, if we knew what that was, then we could solve the system. So what we need to do is we need to make sure that E0, that this system is going to converge to 0, or that this sequence of errors is going to converge to 0 no matter what this initial error is. So how can we assume that? What do we need to assume? Well, what we need to assume, essentially, is that the matrix, the sequence of matrices, I minus L to the power of k plus 1, converges to the 0 matrix. In other words, if we have a matrix and we take higher and higher powers of it, we want that matrix to converge to the 0 matrix. Well, how can that happen? Well, let's think an analogy with real numbers. If we have a real number, or complex numbers would be even better. If we have a complex number and we take higher and higher powers of it, what is the only thing that is going to guarantee that that sequence converges to 0? Well, it's going to be that the modulus, or the absolute value, has to be less than 1. If the modulus is bigger than 1, it's going to go off, its modulus will go off to infinity. If the modulus is equal to 1, and you raise it to the power of k, it's just going to stay on the unit circle. Or if we're just dealing with real numbers, it's going to stay, bounce back and forth between minus 1 and 1, or just stay at 1 or whatever. But it's not going to go to 0. It's only going to be if the absolute value or the modulus is less than 1. Okay, so what is the absolute value of a matrix, right? That is something that is not well defined unless we give it a definition. There's many different things that we could define it as, but for us, what we want to look at is the spectral radius. That is the modulus of the absolute, the modulus of the largest eigenvalue. Okay, so you look at all the eigenvalues of this matrix, you take the one that has the largest modulus, that's the spectral radius. Okay, so the spectral radius, typically denoted as R of I minus lambda. This is the rho of I minus lambda. It's the spectral radius of this matrix. This is going to be equal to the maximum of the absolute value, or the modulus of lambda, where lambda is in the spectrum of I minus L. So the spectrum of I minus L is all of the eigenvalues of this matrix. So we're going to look at all of the eigenvalues of this matrix, take the modulus. If it's all real, that's just going to be the real number, that's just going to be the absolute value. If we're dealing with complex numbers as well, it's the complex modulus, and then take the maximum. And there's a finite number of these. There's always less than or equal to the size of the matrix. So if it's an n by n matrix, there's less than or equal to n of these, so the maximum is a well-defined number. That is the spectral radius. And what we learned in chapter 1 is that a sequence of matrices mk converges to the zero matrix if and only if the spectral radius of the matrix is strictly less than 1. It's not going to work if the spectral radius of the matrix is equal to 1. So this matrix converges to 0 if and only if its spectral radius is less than 1. So in order to make sure this goes to 0, no matter what the starting value is, we need to make sure that the spectral radius of I minus L is less than 1. Okay, so how can we do that? Well, you will show on your, there's going to be, when we apply this to each method, we're going to see how we can determine this, okay? But as you will show on your homework this week, that if we just look at the standard iteration, if we start with AX is equal to B, where A is the Poisson matrix, and we try to do the standard Richardson iteration, AK plus 1 is equal to AK minus AXK. Okay, again, where A is the Poisson matrix, so we don't precondition this system at all. We just take this system as is and try to apply Richardson iteration to it. What you are going to see is that this is not going to converge because the eigenvalues of A are too big. And for A, we're actually, an important thing that we can do with the Poisson stuff is that we can compute the eigenvalues explicitly and exactly. We compute the eigenvectors and eigenvalues explicitly. That's one of the things that you're going to do on the homework, is show that the largest eigenvalue of A here is greater than 1 in absolute value. Okay, so what that means is that this method does not work because, not the eigenvalues of A. You're going to show that the eigenvalues of I minus A are greater than 1 in absolute value. Okay, so this is not going to work then. The Richardson iteration applied to an unpreconditioned system is not going to converge for all initial guesses because the spectrum of this is too big. So the whole idea of preconditioning this system is to take a system like AX equals B that would not converge with Richardson iteration and modify it to an equivalent system in the sense that the set of solutions stays the same so that that solution will converge. And so here's sort of the principle. What we want to do is we want to precondition. So we want to take this and precondition to get to a system M inverse AX is equal to M inverse B. And we want M to have some properties. For this to work, we need M to have some nice properties. But the main one is that we want M, let me write it like this, to be approximately equal to A. Okay, so if you think about something like the Poisson matrix, its diagonal is sort of the big part. Okay, so the diagonal times A, the diagonal of A is kind of like approximately equal to A, in the sense that the error is small. It's not as small as we want it to be, but that's sort of the main part of the matrix. A is D. And so in that limited sense, we say that the diagonal is approximately equal to A. Okay, so obviously this is this needs to be quantified, and we'll do that as we apply each of these methods to each one of these systems. But our goal is we want M to somehow be equal to A. And we also want equations like mx equals y. You want these equations to be easier to solve than ax equals b. So for example, in the Jacobi case, M is equal to the diagonal matrix, and solving this is very simple. We just divide all of the elements of y by the diagonal of d. In the Jacobi and Gauss-Seidel, M is a lower triangular matrix, and it's much easier to solve a lower triangular matrix than it is to solve a general n by n matrix. Okay, because if M is just as hard to solve, if mx equals y is just as hard to solve as ax equals b, this doesn't make any sense. Okay, it might make sense from the iterative method standpoint. We might get an iterative method that converges faster. I mean, you could just take m is equal to a, and okay. But from a practical standpoint, if this solution is not, if this is not easy to solve, significantly easier to solve than ax equals b, then it doesn't really make any sense. And when I say significantly easier to solve, I mean like if we have some method ax equals b that it takes O of n cubed operations to solve. This needs to take like O of n operations to solve, or something like that. So a like sort of qualitatively less time in this sense. Okay, because notice what's going to happen. If M is approximately equal to A, then it means that our new matrix L, which will be M inverse times A, so over here, like for Jacobi, M would be equal to D, M for Gauss-Seidel, M would be equal to D plus L, and for the SOR, M would be equal to D plus omega L divided by omega. If we precondition and we get some system like this, and M is approximately equal to A, so then M inverse is approximately equal to the identity matrix. Okay, so let me say that one more time. If M is approximately equal to A, then M inverse A is approximately equal to the identity matrix. And again, these are just heuristics when I say that approximately equal. When we analyze each scheme in more detail, we'll quantify this, or a way to sort of quantify this. Anyways, L, M inverse A approximately equal to the identity matrix, then what this says is that I minus L is approximately equal to the zero matrix. In other words, it's small. So the whole idea here is that we want to precondition with a matrix so that in that preconditioned system, this matrix here, I minus L, is going to have better convergence properties. Okay, now the last thing that I want to mention, this matrix L is called the iteration matrix, or sorry, the matrix I minus L is called the iteration matrix, and a very common way to denote it is with a capital T, and then whatever, something here to denote what the method is. So like, if we look at T sub j, then the iteration method for T sub j, the Jacobian method, is going to be I minus D inverse A, and then for Gauss-Seidel, this is the only one, the next one that I'll do, T is going to be equal to I minus D plus L inverse A. Okay, and so then what we're going to do is see how we can analyze the spectral property of these matrices right here, and see how as we go from Jacobi to Gauss-Seidel to SOR, we're going to get better and better convergence results.